So we have to go to a catalog and select an expansion joint that can handle a total lateral offset of 0.9 squared plus 1.02 squared squared sum of the squares. That's about 1.4 inches. Let's go back to the PowerPoint. We see here that if I do that math, I get about 1.37 inches. What 8-inch expansion joint can handle 1.37 inches of lateral movement? Well, I'll go to the catalog. This is Senior Flexonics Pathway Catalog, 8-inch, 50-pound class, non-concurrent movement. Look at lateral. What number is above 1.37? Well, looks like 20 convolutions. I would imagine maybe 18 convolutions might work too. So that's going to be the one we wish to use here. We want to select a 20 convolution expansion joint tied. It's rather long though. It's the overall length, including the weld ends, is about 18 inches long. I believe the manufacturer might talk us into buying a tied universal joint because it is such a large lateral travel. But right now we're going to work with a 20 convolution joint. Now, when we wish to build that in the model, we have to worry about one other item here in our input. This term here, here's our axial spring rate, our lateral spring rate, and here it says angular spring rate. Is that the number we wish to use in Caesar 2? And there was a discussion in the write-up about whether to use this number or not. Is it bending flexibility? Is it bending stiffness? So here's the exercise that will work through this. Is that the right number to use? That's 76. If we go through the math, the bending stiffness of that expansion joint is 306. It's 4 times the size. If I'm using a zero-length expansion joint, I'll use a 76. If my expansion joint has length, it's a flexible element, then I'm going to use 306, 4 times higher. Now, to allow you to digest that concept, there's another model in your machine called Bend Flex. Let's take a look at that model. Remember, 76 and 306. So back to Caesar 2. I'll close out this output, and we're going to open up the job called Bend Flex. Open Bend Flex. We see we have 3 separate models here. Let's open that up, get them on the screen, go to the input, and let's close out that plot. They are, and I've put on labels. This is a flexible length joint, this is a zero length joint, and this one has no bending specified. So they're very simple models. If we look at the PowerPoint slide here, the first model, the entire run is the expansion joint. It has length. And what we're going to do is we're going to put a 1-degree rotation at the end, the free end. We're going to do that for each one of these and see if we get similar numbers or what type of numbers we get. The second one is a zero-length joint. There's an element from the anchor to the midpoint and a second element from the midpoint to the end. And in between those 2 elements, there is a zero-length expansion joint. So the flexibilities go at that location, but there's no length to it. And then finally, the last one will be an expansion joint with no bending stiffness specified. So these are identical, but this one has no bending stiffness. Let's see what the program does. Because when we say to put an expansion joint, we usually recommend you do not specify that bending stiffness. Let's go back to Caesar 2 and look at them a little closer. Here's 10 to 20. That's that whole run. There's our displacement at the end. And here's the expansion joint. I'm putting in 306. That is 4 times 76. So bending stiffness is 306. We'll confirm that. On the second model, 110 to 115 is the first half. The next element is 115 to 116. It has no length. This is a zero-length expansion joint. It used to be very common in pipe stress analysis. But here's the expansion joint. There's the same axial stiffness, same transverse stiffness, and here's the number divided by 4. This is a number from the catalog. This is bending flexibility. Torsional stiffness is very high, and the effective ID, we don't have any pressure on the line. This was put together from the hand calculations here. So that's the expansion joint by hand at a point in the system. The third one is the same as the first one, except there is no bending stiffness defined. Let's check this one again. Yeah, same data here as the third one, but no bending stiffness is defined. The program can calculate that for you based on the length, better be correct, and the transverse stiffness. So again, the load case is just that 1-degree rotation at the ends, and I'm expecting to see if these numbers work right, get the same load on all 3 of them. So let's do the error check. And here the program is giving a message for the first one saying that, hey, you have a flexible length defined and you are defining both the transverse and bending stiffness. It's permitted, but you may be getting into wrong numbers if you are using the catalog value for that bending term. With metallic expansion joints, the program can calculate one of these two. It goes on to say that, well, rubber expansion joints work differently, and there you would specify both transverse and bending together. Click the running man, and here we are in the output processor, and let's take a look at the restraint summary extended. This will show us both the load on our boundary conditions and our displacements. So our first element is 10 to 20, and use a negative sign here. Now I can see all of my loads and my deflections. So 10 is the anchor, free end is at 20. I want to see the 1 degree rotation. Let's do it this way. Let's look at displacements first. Displacement is at 1. Just to confirm the numbers we put on them. There is the 1 degree rotation at 20, 1 degree rotation at 120, and the 1 degree rotation at 220. Those are the three ends. The output says that they all move down the same amount, about 1/10 of an inch. So mechanically they're operating the same way. What about loads? I'll look at the restraint report. And on the first element I get 77 inch-pounds, second one 76, and the third one 77. So yes, those three expansion joints are all operating the same way. So you have a choice in how you define these components in Caesar 2. Now one last point on this exercise here, if I go back to the PowerPoint, this is a review of another slide that was in the previous session. I just thought it needed a little more reinforcement. Caesar 2 uses the effective diameter of the expansion joint. Let's go back to the input here. In order to put a pressure thrust load on the expansion joint. So in our model here, there's our effective inside diameter, 9.440. We get that number from the catalog, expansion joint catalog. If I go back to PowerPoint, we'll see that. Here, the effective area is 70 square inches, so you do the math to get the effective inside diameter. Now, Caesar 2 will use that in order to put the pressure thrust on the line. What Caesar 2 will do is apply the pressure thrust on either side of the joint, when in fact, it would be better to redistribute the loads in this fashion. Here's my effective diameter, so we have that area times the pressure pulling on either end of the expansion joint. What should happen, and in some cases this may be important for you to remodel this, if I look down the pipe and I see the surface back here, this is just the inside of the pipe. That would be the load applied out here. If I look the other way, I don't even see the load on the nozzle. I see the load on the back of the pump casing or on the impellers, and that will then go down to the anchor. There's really not much compression on this side from pressure thrust here. The remaining part of the load, the effective diameter minus the inside diameter, this annulus surface here, is what would truly be applied on either end of the joint. That's the difference between the inside of the pipe and the effective area of the joint itself. So if you wish a more detailed model, it would be up to you to remove that effective pressure thrust on either side of the joint and apply it more accurately through the model. All right, on the next session, we'll talk about selecting a joint and then installing it in the model.